Abstractions and Codification in Software Engineering lecture by Mary Shaw from 1984. What's this about? Hello, I'm Chris. I'm a KMP developer. TechSport said they're coming out for that. Right. Today I'm going to be watching a lecture by Mary Shaw, who I found out when I started doing the when I listened to Grady Booch talk about software engineering, and I exposed him in that video. I mean, I didn't expose him. He has a couple good points, but some of this other stuff is like, man, stop. Anyway, so he says this lady was the best about software engineering. So I said, well, let's go look at what she has to say. I mean, Booch is all right. He had some. He's on the right path. It's just he had to make a name for himself and all that. So he's a IBM fellow, you know. So he had to like a little overextend things a little bit, but at least he was trying, you know. So I'll give him that credit. Let's speed it up a little bit. Oh, Unisys. So they were big at the time. Gone now. Grace Hopper's cool. She brought COBOL, but it's again oversold it though, and we're stuck with it now. Can't extend it. Can't figure it out. But better than what better assembly.
Shaw, and she's a professor of computer science and associate dean for professional programs at CMU. Her main focus, as far as research goes, is software engineering, abstraction techniques, and software architecture. And today she'll be talking to us about abstraction and codification in software engineering. Dr. Shaw.
All right, here we go. I'm ready, Booch.
Thank you very much. It's a real privilege and an honor to be standing up here to share with you where I've been and where I'm going. I had the opportunity.
CMU was known at the time, by the way. CMU at the time was known for this. I guess she was probably one of the people behind it. It was awesome. And she definitely looked like a computer science lady. So let's keep going.
Ago, when Grace Murray Hopper visited Carnegie Mellon to chauffeur her around while she was there. This was after her interview on 60 Minutes that gave her a lot of national exposure and before her retirement from the Navy. There are a pair of incidents from that visit that stick in my mind. I picked her up at the airport. She was in full uniform. She was very proud of that uniform. And
yeah,
from
she's
the
cool.
Gate to the parking lot. We must have been stopped by 4 or 5 or 6 people who recognized her and wanted to say something.
The thing I like about Hopper is she was like, you have to make this easier. You have to make this easier for people, regular people to get involved. We can't do assembly language. We can't go down to the bits on every damn thing. We're making this thing work. And we also have to get this time delay. People well known to tell people how long it takes for this stuff to transmit around and compute and all that stuff. We have to get that way more than well. So I'll give her credit for that, because before that, it was you were not, if you were not in the priesthood unless you were an assembly language programmer, and for that particular hardware that they had just made, unless you were like got it right off the bat and were combinatorial mathematical genius, you know, then you could use the machine. But like, that's not really what the machine. That's not the problem, man. That's not being super mathematical genius. What it got us places, but not everywhere.
Something just to be near her.
Without Grace Hopper,
and she grew progressively more and more impatient with us. When we walked into the parking lot, she said, "I have to keep remembering that I'm an officer and a gentleman."
All right. So there was a movie at the time called Officer and a Gentleman. It was very popular. Anyway.
Well, it was an academic visit. And at dinner that night, we had 6 or 8 people at dinner, as one does when a distinguished speaker visits the university. And in the middle of dinner, a young woman came over and said, I'm an enlisted maintenance crew at the base in Hawaii, and I just wanted to tell you how much I admire you. And she had the world of time and attention for one of her people. I thought it was great. She enjoyed working with young people. She thought that young people were the hope of us all.
That's cool.
18 to 20.
A lot of these guys aren't like that. They're like, no, fuck young people. Unless you're elite, you can't even be in my presence. She wasn't like that, so that's awesome.
The young people are more interested, more open, more flexible, and the root and the germ of where progress is going to come from. So it's especially gratifying to see so many students at this conference. I flipped through the attendance list, and it looks like about 30% of the attendance is students. Admiral Hopper would be proud. Anyway, to the students here.
Let the applause run, lady. She stepped on the applause. She's not a stand-up. I can keep going anyway.
I'd like to encourage you to find something here that captivates you. For the undergraduate students, I hope you find something that gets you hooked on the field so that you don't escape into all those other things that people drift off into. And to the graduate students,
what's that mean?
I'd like to encourage you to remember that one of the things that Admiral Hopper did was change topics periodically, so that when you finish your degrees and go out, that rather than sticking narrowly to the topic that you have in hand, that you're at least open to other ideas, some of which you'll see here, some of which you'll see
I did that.
about what to do next. So I've tried to organize what I'll say today in order to try to bring out some of the threads about how I've moved from topic to topic. And you might say I'm easily distracted, or you might say there's a thread that tries to connect it, and I've tried to retrofit a thread.
I don't know about that.
Can I have the next slide, please?
Hopping around.
The theme of what I want to say is that if I look back through the history of software as I know it, that there are a couple of threads that have knitted together a lot of the pieces of progress. One is a thread about abstraction. Abstraction is a focus on certain commonalities that help you do design and help you understand your systems.
Well, I was really always confused with this word term abstraction because this lady obviously is not part of the art world. And I was kind of involved with like messing around with art when I became aware of this term when they were throwing it around in computer science. I was like, are you talking about like abstract art, like this conceptual, weird freaking style of art? Or are you like, are we supposed to be bizarre worlds? Like, no, it just means general. It just means general. The general idea, the general concept, the overall arching thing, not specific.
One is a thread about codification. That is,
that messed me up for years.
I know understanding the chaos, finding good abstractions, and organizing them so that you can find the answer that you need at the time that you need it. We're moving gradually toward an engineering discipline for software, something that we can respectively call software engineering. And I think these are two of the themes about how...
I don't think so. I think it's always going to be catch as you can. What's the best idea? How you can arrange these things in a different way to make it more useful for humans. And it's going to just be a continuous process. I don't know if you can put engineering practices behind it. So because then you just constrain it to this little small box. There may be like areas that can be constrained that way. But that's what we create a library for. So why do we need to do that when we can just create a library for that particular thing? And if you can figure out a problem and a way to solve it, then you're on your off to the horses. Now, if you could put all kinds of things around this stuff to make it engineering-ish, but you're never going to make an engineering practice because the stopping problem, the halting problem. You'll never know if these programs are perfect or not. You'll never know. It's just impossible to know on these Turing machines if it's going to actually fail at some point. So you have to build redundancies in, and hopefully those redundancies have a low margin of error that they don't cross over at the same particular time. And if it's even possible on the mission length, whatever, then you got to do 3 of them, 4 of them. You build in redundancies. That's the only way we figured out engineering that stuff. And that's just like, okay, well, that's not really an engineering practice, but it's like it's a technique to solve a problem. And even then, it's not gonna be perfect, right?
How we'll establish the technical
basis. At some point, they'll all fail,
makes
right?
That possible.
So that's just like we're not. That's the other thing is like this engineering. It's like when you're engineering a bridge, yeah, you're doing the same damn thing over and over again, but it's different soil, different places, different kind of wind, and all that stuff. But it's generally an arch over a structure. So yeah, you better have some engineering practices. You better be super dialed in because people's lives are definitely at stake at that particular thing. Now, like airplanes and stuff like that, you can try and put those things in there, but again, it has to come from the culture. It can't be a practice that's imposed. It has to be a culture of caring about that stuff. And if the culture doesn't care, you can skip all that stuff. Right? It just gets gamed, right?
So what I plan to do today is begin by talking a little bit about the character of engineering disciplines and connect that to the engineering discipline of software. To talk about an example
I appreciate the attempt
that shows how chaos has led to abstractions, which have led to well-organized and well-codified
chaos. You mean there's just people figuring out what to do with these damn things, these damn computers, how we can apply them to human problems? Chaos? No, that's innovation.
Knowledge, and that's abstract data types. And to pick the example that I'm currently excited about, which is software architectures, and show how we're at least beginning that process again. So let me begin by talking about engineering.
It's more conceptual than this engineering thing. It's more like how do you approach problems in a way that people, you can still help people, and we can get these machines involved to reduce the repetitive stuff, communication stuff, and processing of something and stuff. Is it possible? That's really the engineering, if you want to call it that, is a philosophical, cultural approach to a problem set. And finding a way to use these machines to help people with that problem set. How else you would describe it? It's not really an engineering thing. It's more like, I guess it is, but it's not an engineering practice. It's more like social. It's very social. Like computers, as much as we don't want them to be, they're very social things. If it hasn't been obvious, they're extremely social. So this whole social thing, like for people, right? For people. Okay, keep going, Chris.
I took a sabbatical a few years ago and spent a good deal of it reading the history of engineering. The reason that I did that was that it seemed to me that the work that I was trying to get started at the time had the flavor of trying to establish an engineering basis for doing software. And I thought it would be useful to understand what an engineering basis for doing something else was.
All right.
If you read history of engineering, you'll stumble regularly over definitions of engineering. And the definitions have a number of...
It's finding techniques, the discovery of techniques to solve problems that humans have. That's engineering. It's and there's like a set of techniques that work for things that can be applied, but that's not the only set of techniques. Those are just the known things, right? There's those unknown set of techniques which are being explored at all times. Most of them are wrong, of course. Most of it's wrong. Most of the stuff that got to the core techniques, most of that was wrong at one point, or totally ignored, or frivolous.
Terms that show up over and over and over in the definitions. Engineers create cost-effective solutions. That means they're concerned with what the client needs. The client has economic constraints and needs not...
Yeah, you can't move. You can't have all the gold in the earth, and we solve cancer. It's like, okay, well, if we could do that, I don't know, maybe we could do that. But at the end of the day, you'd have to actually solve cancer because it's going to be a lot of effort. Because that's what economics. We're talking about economics. Yes, solving problems economically. Because the problem, the thing is, it's like you find a problem that you want to solve. It's like, well, can you support? Could you have customers, enough people interested that'll pay you to support you doing this thing in a long term, or is it just a hobby?
Solution, but the solution that is good enough and affordable.
You're doing it out of the goodness of your heart, which is like a lot of stuff. But if you're going to rely on it, people are going to rely on it. They kind of want to have a structure there that they can rely on. That means you got to have in this particular universe, you're going to have a company or some sort of thing where they can pay you to support you, so you can eat, put your electricity on the internet, live in a place, and have a life that's worth living more than what they can just do, flip burgers. Come on, yes, it's economics.
Cost-effective solutions to practical problems. Engineers work by and large on problems that people care about, for which the solution will be useful if you can create it. Engineers work by applying scientific knowledge.
Exactly.
Not all.
If you can create it economically, right? That somebody was willing to pay for and support your efforts on an ongoing basis, because we all know that if software is never killed, it's just abandoned. Projects are never ended. It's just abandoned for temporarily until they could last infinite amount of time. They're never. I mean, it's just do people care about this particular thing? And if not, they're done. And let's moving on to the next. This is human engineering. This is how we do it.
Engineering is applied science, but one of the marks of an engineer is that an engineer reaches for a well-organized, well-founded scientific design or analysis or strategy whenever there's one available.
Oh yes, for sure. If we can use a library that's going to do SQL for us, and we don't have to pay a licensing fee, and somebody's gone through all the engineering trouble to reproduce all that stuff and make it useful and free, oh yeah, we're using that. But before that, $1 million contract. And that was economical, because it's going to cost you at least $1 million to roll your own one of those things. If you're going to hire your programmers on to then reproduce what they, I just pay the fee and pass the cost along to my customers. There it is. It's all economics.
And it's largely the infusion of a scientific basis into a discipline that changes it from a craft to an engineering discipline.
It's all scientific, right? You think the engineer thinks he can solve a problem. He goes and tries to do it. Most of the time fails, but he might actually get something, and then he can just give it to his other customers, reproduce it for his own customers, and maybe sell it to somebody else as a package solution. They can then go run it and get their own customers. Like, well, this is
discipline. Engineers.
That is scientific, by the way. It's hardcore science too, because you're proving a hypothesis by having people buy into it literally by paying you for it. So it's not like, oh, it has to be in a lab with a head scientist with PhD. It's like, no, everyone's doing science all the damn time. Just figuring out what works, man. It's not this high and mighty holy thing. It's like an academic thing. Yes, there are aspects of it that are rigorous, that need the aspects of research or investigation, but this building products for people is very scientific.
I like build things, and I'm
because if you fail, it doesn't work, and you don't have any customers, and you go out of business. It's not rocket science, right? You have something, you have a hypothesis, you think you can solve something some way, you create something that does it, and they show other people, and if they buy it and they keep you sustained, well, you just solved something. If you don't, well, then you didn't.
Open-minded enough to believe that developing software is building things. And most definitions of engineering include a term about engineering in the service of mankind.
Yeah, always.
The thing about this is that
you're not going to just do a service of ant kind. Oh, guys, maybe somebody out there is writing some software for ants, but it's definitely a hobby. They're not writing checks to support you. Come on, lady. Come on, let's keep
engineering.
Going. Hey, I'm gonna be a little hard on her because it's funny. Also, I'm looking at the retrospective, what, 40 years ago, 30, 35, 40 years ago. So
ordinary people
I get the high horse, and she doesn't get to defend herself. So that's whatever. It's for your entertainment, okay?
to do
I hope you're laughing.
things that formerly required virtuosos. Maybe virtuosos can do it from their soul. Ordinary people need help, and engineering is a way of organizing systematic knowledge to help people do that.
Correct. Yeah, they want to outsource it to you. Look, man, if people could make their own drones, they would. But the fact that I can't do that, I mean, I could if I wanted to with all the remotes and the open source and all stuff. But somebody else went through the engineering too, and then somebody went through some really hard engineering to get those little sensors to work that way and the motors to get all sequenced up and all stuff. But if I can just give DJI or whatever, one of these drone companies, $1,000 or whatever, I get all that technology and I don't have to go through that whole stuff. And all I want to do is fly the thing anyway. I didn't really want to go through and learn how drones work and all the altimeters and pressure sensors and gyroscopes and all. I don't. It's cool, everything. I mean, it's nice to know how stuff works, but I don't really want to fine tune it and 5,000 test flights till I get it right. No.
So there's some characteristics of engineering practice. Engineers iterate between analysis and design.
Yeah.
They generate.
Does this gonna work? Maybe. I don't know. There's only one way to find out. It's to run this experiment. You gotta be a little crazy to do it that way because everybody wants this guaranteed path. Wouldn't it be nice if you just know ahead of time if something's gonna work or not? Just know ahead of time, just think it up in your head. Nope, you actually gotta put it into practical. You actually have to put it out there. You have to write to take a risk. Better plan, get a deck together, get somebody to finance you, or just you're gonna use your own money to finance this damn thing and spend your own time, ramp something up, and hopefully you got something up before somebody else has the idea too and rushes you to market and kicks you out of it. Yeah, this whole thing's going on the whole time. What's going on?
Create multiple alternatives and consider their trade-offs.
Yeah.
Usually in a practical.
The trade-off is this. If this is close, or I'm not even in the ballpark, and people will tell you, like, if you're close, if you keep doing this over and over and over again, and you fail, it's not really fail, it's just an experiment that you thought was going to work didn't go the way you thought it was going to go, and you had this other result, you get feedback. Hopefully you're doing this in public and not just keeping them to yourself. That's definitely a death now. But you put these things out there and show people and see if people feedback on whether they like it or not.
Problem to find a cost-effective solution, you have a lot of constraints, and the constraints.
That's how all this stuff happened. All the stuff we take for granted, Linux, Unix, it was all just somebody experimenting, showing other people. And then the stuff that the people that experimented and didn't show anything, that went nowhere. And there was definitely lots of guys like that. Lots of guys that would just not show their thing because it's a real special thing, and it went zero. There's lots of guys like that. Lots of innovations that at the time would have blown up and could have made it. But because they were doing this proprietary, hold on real tight, and not doing this socialization, talk to everybody about the thing I found.
The iteration between analysis and design.
So there's this thing where you actually have to put it into the real world. Like there is this type of science where you can just do it in your own lab, in your own basement. But eventually, I know it's hard to admit this, but you're eventually going to have to show somebody else. And they're going to have to see what you're going to have to give them enough information so they can then do what you did. So they can redo what you did, and this is science. It is possible to have a breakthrough on your own and keep it for yourself, but that's not really science anymore. That's something else. It's like black budget project. I don't know.
And the decisions about trade-offs between alternatives is involved with deciding how to balance the conflicting constraints against each other.
Yeah, of course.
Engineers make heavy use of.
Am I gonna be able to make this in time? So I can make a paycheck from this? That somebody will pay me enough? Can I keep it going? Do I have enough savings? Do I have enough runway to keep going, to keep this thing, to see if there's even a market for this stuff? And most people don't even try that. They're like, fuck that. I don't want to do all that stuff. It's like, well, then you're not really solving people's problems. You're not really doing engineering.
Earlier designs. They get the earlier designs from their own experience, as we all do. They also rely very heavily on handbooks of good engineering.
Really? Where else would you get it, lady? Where else would you get it from? We're going to read a book. Oh, look at this. I have all the information I got from, instead of doing 1,000 experiments. Where else do you think we're going to get look, man, the engineering thing isn't for everybody. It's for people that are like super curious, bludgeons for punishment, can repeat stuff over and over again, are willing to go through and be very mentally challenged and think you're complete retard until you figure it out. That's the stuff that most people give up. Most people do not want to spend that inordinate amount of time in pain, in confusion, And then trying stuff and then it doesn't go anywhere. And then doing it again. What are you, crazy? Yeah, a little bit.
Practice, which have examples of previous designs and rules about the scaling limits of the designs and which designs work in which situations and which designs don't work in which situations.
Random as hell, man. It's random as hell. It's so random what people want and what what you show them, and they're like, nah, that's not it. It's like, well, you asked for that. It's like, nah, I don't really want that. That's not how I want it. Well, how do you want it? Okay, then you're in the process. Then you're in the loop. No, we get closer over here. And then it's like expecting someone to like, oh no, that's the perfect thing. I thank you for giving it from on high, from bringing it from God down to the human beings. It's the most perfect thing ever. Doesn't work like that. Come on now.
Rely on catalogs of parts. They rely on.
But they want it to. These business guys really want it to be like that. They talk about it like that because all they see is these factories that have been built, the machines put together, designed, and to create a widget that people want, and they're solving a problem. They see that part, but they don't see this other part, which is fail, experiment, didn't go right. No, that's dumb. Why'd you do it that way? Nobody wants this. Oh my God, am I going to do this? Am I able to do this? Maybe not, probably not. Odds are no. You keep going anyway. And that's when we get, oh, wow, how did you come up with this? Well, I did about 17,000 experiments over the period of 22 years. And eventually I came up with this. And I kept going. Whereas most people are like, I got life. I got to live a life, man. I got other things to do. Chase girls, play video games, watch sports, do exercise, raise kids. Not be obsessed with something like this. You got to be a special kind of like. Look at this lady. You think she's like, oh, I'm going out partying on the weekends? No, man. This is like, first also of all, obsessed. But this is the best thing she's got going on. This is the thing. This is her thing. Trying to do this stuff. And this is the kind of people that show up for this. I don't know what to tell you.
Of organized knowledge that's not organized as scientific theory, but that's organized as you wanted this? Yes, here's how you find one. And engineers take a pragmatic approach to cost effectiveness. Again, not the optimal, but one that's good enough.
Yeah, am I going to be able to afford to do this? Or can I just play with my drone and go out and do something else for my own purposes, for my own? So that's the other thing too, is you got to be like this kind of obsessed with like wanting to like help people and like see them being helped by your thing. And not change the world, but change their life. Make their life a little easier, a little more fun, a little less expensive, etc., etc. You gotta have a little bit of like, wow, that's cool. Not just like, I want to get a paycheck. I want to get paid. I won't get paid. Like, you're not gonna make it, man. Look, you got to go through so much failure. There's like, if you're just trying to get paid, there's other ways to get paid. I'm sure that would be easier, but like not as annoying, not as frustrating, not as full of like endless failures. Like most of the stuff you do, nobody gives a shit. Nobody cares. Like, I did it for you. It's like, we don't give a crap.
That's often the difference between timely delivery and irrelevant delivery, by the way.
Yeah.
So here's a model of the evolution of engineering disciplines.
Exactly.
That's drawn from my excursion into the history of engineering.
Let's hear it.
The exploitation of some technology often begins as craft.
Always tinkering, messing around, goofing around. Well, all those people that were all killing all the motors and all the so all the motors and planes and rocket stuff. And not to bring up Nazi Germany, but okay, we're into the video enough. Yeah, we're going to it. Yeah, so the Germans, the reason why they had all those crazy spacecraft and rocketry and model airplanes and remote control cruise missiles, all that stuff back then is because in the 1920s, after the World War I, they said they were not allowed to have an army and all this other crap, and they were like, okay, well, we're going to make all of our kids super into model airplanes, model rockets, and have all these events and all this money spent to have a whole bunch of kids get interested and get pushed into aeronautics and rocketry. And there was a major push, and that's what happened. So all the kids grew up, and guess what they made? Airplanes and rockets and tanks and cars and trucks and all kinds of stuff. So that's where that started. And yes, that's where it comes from. It comes from craft.
The craft practice is informal, it's intuitive, it's often local. And the craft practice persists until that isn't good enough anymore. Until
Correct.
You need more of it, you need it faster, you need it more efficient.
Correct. And there's usually there's this evolutionary process. That's where electronic stuff came from. I was involved when the microcomputer started coming on in the 1970s. I was a little kid. I saw it coming on. I was like, oh my God, I got to get this. And everyone was like, what are you doing? But there was no push. It was just me, like, maybe I'm just reincarnated, one of those people, reincarnated, coming back saying, hey man, I want to still play with the gadgets and apply these things for people. I was always for people. It wasn't for my own fascination. It was always, I was always thought in my back, how will this help and provide value to people? It's always just been there. I don't know where that came from.
At that point, production considerations enter, and you bring production and management expertise to develop a commercial practice.
Well, you make a business out of it.
The commercial practice can be a stable, repeatable commercial practice without truly understanding the basis of the technology.
Yeah,
and it often runs up against difficulties that...
Yeah, of course. Do you think everyone at Polaroid understands all the chemical processes involved in making an instant camera? Lady, what are you talking about? No, they want to do accounting. They want to have their 401k. They want to go on vacation. They want to have office parties. They want to have... Come on. Of course they are. They don't know the lenses and refractions and chrome and different coatings and all the polishing. You think all the people at Polaroid knew all the camera companies know all that stuff? No. Come on, it's business, lady.
You'd like to build this, but you can't explain how to do it.
Right.
At that point,
a lot of it's tacit knowledge. A lot of it's trade secrets. Even the computer software stuff. A lot of it's kayfabe. A lot of it's stock pump schemes lately. Well, they're popular as hell. Like, no technology breakthroughs. Well, we'll pump the stock we'll tell you a bunch of lies and AI is taking over everything. Really? AI is taking over everything?
It often triggers the development of an associated science. Chemistry certainly started that way.
Yeah, for sure, man.
And as the science becomes more mature, it starts feeding answers back to engineering.
Yeah, it's all the hobbyists and geeks and nerds and weirdos playing their little things, exchanging notes, by the way. If there's no notes being exchanged, you're not giving it to other people, getting them in on it, because that's how it is in the beginning of these things. Chemistry, whatever, electronics, whatever, we're all just sharing notes back and forth. Woz gave away the Apple One. Here's the plans, public domain, there you go. You can build your own. They're like, we don't want to build our own. We want you to build it.
To science. And when the science is sufficiently mature to be regularly and systematically feeding answers to commercial practice, then you have a full practice of professional engineering. I'd like to elaborate that a little bit. And let's put this picture up on the side for reference. And I'll kind of walk through some of the pieces. The craft stage is characterized by virtuosos and talented amateurs. People do it because they just understand, or they do it informally and not necessarily very well.
Better than anything at the time, better than anybody else was doing. What are you talking about? He was a talented amateur, man. He's been making computer games since 12, 7, 8, 7, I don't know, a little kid. We should take down the Washington Monument and put up the Woz Monument. And while that guy's still alive, because without him, we wouldn't have half the stuff that we have right now. The guy is a national hero. I'll keep going.
Force. Progress is haphazard. There's not any systematic way of communicating progress, and so people reinvent things over and over again.
Of course.
They share only very locally and not very systematically what they've learned. They may make
there's no network yet. There's no business associated. People are like, this is weird. Why are you guys? It'd be like somebody inventing a card game, inventing a card game, and then they play it locally amongst their people. It's like, what do you expect a network of card players to show up immediately? It's like, no, nobody cares about this thing. This is a silly game for kids. But no, a bunch of people start playing. It's like, it's a super fun game. It's a silly game for kids. But adults like to play it too. Oh, wow, really? Okay, and that's how all this stuff happens. It wasn't, we're going to make the computer industry and we're going to create a network of business associates. Like, no, it wasn't like that. It was like, we're trying to make computers for ourselves instead of using a terminal to log in, which we don't, it's super expensive in itself. It's like, well, I was like, whoa, you have the computer right here. You can type in, log in. You don't have to log in anywhere. And have the video right here too. It's like, holy shit, what? It's like, you could just make your own. It's like, make my own. I'm not one to solder. I suck at soldering. You burn the chips and everything's double jointed, cold soldering. I have to learn a whole other skills. I know. I just want to learn the computer thing. Well, I was like, really? And then Jobs was like, yeah, we can sell these puppies. And here we go. He's like, he started listening to the customers who were like, I don't want to solder this damn thing. I want you to do it. I don't want to drill out the board. Drilling out the board? No, can you do it? For $50 you'll do it? Here's $50.
And things are often produced for use, local use, not for sale. Does this sound familiar to anybody? Okay, at some point, the technology is too important for this to work. This does community barn raisings. And many traditional house building community activities have this flavor. There's a ritual.
This is America. This is how America did it. That's why I came here, because this is the culture of the tinkerer, of the we tolerated the weirdo, and he'd come up with some weird stuff. Yeah, a lot of times it's crap, Doesn't make any sense. But every once in a while, one of these guys came up with like the airplane.
That you go through that yields a perfectly serviceable house, but it's not an industry. Well, when you bring production skills to the party and develop a commercial practice, then instead of having people doing it ad hoc, you have skilled craftsmen, currently craft folk, I think, who follow some.
And that's where they all come from, by the way. I don't know anybody that just jump into computer science without tinkering with stuff that they're on their own, making scripts or whatever. You think anybody that got into computer science just oh, I'm getting into computer science now? I mean, maybe some did, but that's not going to last very long because the tinkering thing is like 90% of the goddamn job is figuring out how these things work, what's possible, what's not possible, what the bugs are, limitations. And do you think you're just going to read the manual and they're going to tell you that?
Established procedure. The refinements may be entirely pragmatic. For example, steam engine boilers were originally built with flat sides. And through observation, they figured out that maybe round sides were better. Because when you put too much pressure in a square-sided boiler, it bulges and looks around not too long before it explodes.
Yes.
That's pragmatic.
You develop engineering practices. Yes, absolutely, 100%.
The skilled craftsmen are trained in mechanics.
Other studies, other practices can be used to enhance yours. Some other knowledge that's basic engineering about how to put these things together. Oh yeah, hell yeah! Anything you can apply, just apply it. Yes, the more popular it is. If you have a card game that has an extension, like a deck that automatically shuffles it for you, yeah, of course, I'll put all that stuff in there. Yeah, but that starts. We gotta have people playing, right? You have people in that field, and somehow making money, or money's gonna be on the horizon somewhere because this stuff takes major time and effort. Now the tinkerers are doing it because it's fun. But once you're in the business, you better have some paying customers somewhere to put up with this baloney because it gets real redundant after a while. Running a business, some people love it, the maintainers love it, but people that are tinkerers, creators, we just can't deal with that. We have to be going into another thing, building something else somewhere else, but we can't be running the business. We suck at that, by the way.
But more or less by rote. And the concerns about economics are concerns about supply and demand and how you produce. Here, your manufacturing is primarily for sale. Now, as I say, intuition runs out after a while, and then you need a science. And when the science becomes mature and starts feeding answers to the...
But I don't know if that applies to this computer science stuff, what they call computer science. This is more, it should be computer social science. It's not this engineering thing. There's like computer engineering layer, which is the hardware, and maybe some of the operating system stuff, even though that software layer of Linux, Unix, still, we can go beyond that. That was great for the 70s. Now, we're in 2025. We could probably move away from it at some point. But anyway, let's keep going.
Engineers. Then you have, in addition to the production personnel who are trained in the mechanics of the production, you have educated professionals who can do the design, the analysis, and the projection about how something will perform once you've built it. They're educated in analysis and theory, and now progress begins to rely on science.
They were tinkerers too. They were figuring all that stuff out. I guarantee that.
If I can analyze and make predictions about how something will behave, then I can play exploratory what if. The educated professionals can then enable new applications through analysis. This may actually lead to market segmentation and the creation of niches. So there's a whirlwind tour of the history of engineering.
Yes. So we need big motors and little motors. We need tiny motors. We need electric motors. We need gasoline motors. We need diesel motors. We need alcohol motors.
And the question now is, so what about software engineering? Well, software engineering is a phrase that was coined in 1968 as the title of a conference, and it was coined as a rallying cry. Its purpose, the purpose
justified, because if we're in an assembly, you better have some way of dividing that work up to do all the stuff that they wanted to do in a way that didn't fail all the time. Yeah, you better have a way of. You just can't do raw assembly. You're just not gonna. It's just not gonna get there. And with multiple people working on it, you're gonna have to break that shit down. Yes, and you need to practice for that kind of stuff. Yeah, but yes, once the problem is defined and it's well defined within reason, yes, you could do engineering practices around that. I'm sure, like lots of test inputs, lots of building all kinds of test rigs and all that stuff. But the idea of like how to approach a problem, I don't know if you can create an engineering practice around that. I think we'd already have it now. I think it'd be already codified if we could do it. We wouldn't be discussing how do you do this? We'd already just know. And it's not, because it's all the problems that humans have, and there's all kinds of ways of approaching them, and ones we haven't thought of yet. How do you put container around that?
Attention to difficulty in producing stable, reliable, cost-effective software products. And I can dig those proceedings out and read paragraphs to you that will sound like they were written yesterday.
Yeah, it's the same issues. Because we haven't solved this problem yet. I don't know if it's solved.
The requirement underlying the phrase is one that we recognize. It's a requirement for cost-effective solutions to practical...
It's sort of like asking, how do you build a house without a hammer and without a screwdriver? No, you have to have a screwdriver and hammer. We have to do that. And this is the thing. It's like we can't just jump over the hammer and screwdriver and just house. Or maybe you can 3D printing. I don't know. Maybe there's a way around it, right? Like we could just skip over it. But in general, we're going to have to use hammers and screwdrivers to solve these problems, which means we're going to have to break down our problem into smaller problems that are manageable by one person or one processor or whatever the thing is. You have to break it all down. Let's keep going.
Problems. And the scale of the problems is much larger now than it was then. It was large enough in 1968 to draw attention. So the problems are at increasing scale, which is a sure sign that these systems are not going to last very much longer.
Assembly language, increasing scale. Yeah, you get over. It's just crazy how it's all put together. No wonder you definitely have to have an assembler. You can't write the machine code by hand anymore, so you got to use an assembler. You got to have APIs and interfaces between these groups of people. How this information is stored, some kind of commonality. And even then, it's going to be a clusterfuck.
Longer. The technical basis that serves as the source for the science to support the engineering discipline is, of course, computer science. So I'd like to give you just a few vignettes.
It's not a discipline. It's a set of ideas. I don't think it's a discipline. I think to call computer science a discipline is a disservice. It's not. Computer engineering, maybe, but not computer science. Because we would have a bunch of tools that did all the things that would be engineering around these software projects. Maybe they just don't exist because I don't think it's possible. So let's keep going.
Of the software development situation, to try to emphasize the difference between a simple program and a software system. I don't want to dwell on these. I picked these out of a much larger set.
Every line's a bug. System and a, what did she say?
Difference between a simple program and a software system.
I mean, a simple program runs on a software system. I don't know how. See, all these definitions are trying to like define what these things are when it's just continuum. It's a set of ideas, a continuum of things. We don't really need to have a lineation. It just starts here and ends here. It's like, this is a program and this is a system. It's like, I don't think that's a fruitful discussion.
I don't want to dwell on these.
Okay, so we picked it, but is it universal? We're going to go proselytize the use of universal cutoff between a system and a program. See, that's just, okay, this is like what they call bike setting. It's like talking about the wrong issue.
Larger set, just to try to set some context. First, the demand for software grows exponentially. The chart shows in the steeply ascending line the onboard code size for manned spacecraft, and in the flatter line, the annual programmer productivity growth. And you'll notice that they're...
What is productivity? What are you talking about? Lines of code? We can KPI the shit out. We can PK hack that thing. We can show you lines of code. Is that what do you mean productivity? What does that even mean? How do you measure productivity, ma'am? I'm being facetious here. You can't measure it. Does the problem get solved with the thing we have now or not? If not, what can we do to improve it, or we change it, modify it to make it better to try and solve the problem that we're going to solve? Does it do it or not? Do we have customers or not? Does the spacecraft fly, or does it explode on the site?
Diverging. You'll notice also that the vertical scale is a logarithmic scale. That means those are really exponential curves. The software size curve is compounding at a rate in the low 20%. The productivity curve is compounding at a rate in the 4 to 6% range. This is the famous Barry Bain 4 to 6% productivity growth number.
What does that even mean?
And what that says is that not only are we falling behind...
How's he measuring that? How's that measured, ma'am? Do they just scalp? We're talking lines of code? Efficient, like a schedule versus what we expected versus what it actually came out to be, given all the conditions and restraints and error codes and libraries not being compatible and systems not integrated, undefined regions of the edge cases.
We're falling behind faster all the time.
Falling behind? Well, falling behind compared to what? I'm definitely a no estimates guy. I'm like, we have a month, or we're given 3 months. You have 3 months. Show progress, real progress towards it, or program ends. You're done. And that's kind of how it is anyway. People might say, oh, well, you have 3 months, but we only have 3 months one way, so I'll just tell them 3 months and we get it in 6 months. But there is an end point, right? There's an end point, because every company I've gotten to, they don't provide the solutions to the problems on time or in the period of time where they were allotted. And
so demand for software rises faster than the production capability, and the growth of system size you can expect to regularly outstrip the scalability of whatever technique you're using right now. So you've got to keep looking for new techniques, and you need to look for new techniques that will contribute to productivity.
Here's for Chris from the future. We're still looking.
The
We're
next
still looking,
snapshot is to
lady.
remind us that producing software is not a local activity anymore. We are becoming increasingly connected. This is recent data on how well connected the world is.
There we go.
There are 235 or 240.
Internet was super new then. It was just basically the connections between file transfers and some Usenet, some email list stuff. It was very, very basic in '94. Very, very basic. It was just starting to get the hypertext stuff coming online at that time.
Countries here, but are actually international political entities. I think the Virgin Islands is one, for example. And this shows how many of them are connected to the international network in some way. This means we're not only going to be designing distributed systems, but we need to design systems in the network context so that they will be usable by people who've never seen them before. We're going to see a marketplace, I think, in which components are marketed.
That was good. But then kind of was in '94. We kind of knew that already, that we're not going to do in command lines at this point. So it wasn't a major stretch for her to say this. We had lots of GUIs happening. It was a major thing at that time. So, and making things simpler. We'd had AOL since the '80s, late '80s. So people kind of knew, like, that, yeah, we're gonna have to, if you're gonna have more people involved, we're not gonna, you have to make it super simple for them. So yeah, it wasn't a big stretch.
Frankly, there is much more heterogeneity and much more openness coming than we've ever seen in the past.
Yeah, standards, protocols.
Is
check out those slides.
Maintenance. The word maintenance is a misnomer. In the chemical industry, it's maintenance when you shut the plant down and scrape the gunk out of the pipes. In the chemical industry, when you say, let's double the production capacity and change what we're producing and use all the old equipment at the same time, that's not called maintenance. That's called a new development project that's very hard.
Yeah. Yes.
Well, we call that stuff maintenance.
Yeah. Well, you try and call it maintenance because that's how you get the costs. That's how you get past the auditors. Like, oh, we're just doing maintenance. It's going to cost $22 million. We're revamping the whole system. Well, we're going to call it maintenance. No, that's the new system. But to get the line item to be available, can't do anything new, but we got to maintain the old one. It's broken. It's not working no more. It's like, okay, well, you're allowed to maintain it then.
Accounts for well over 60% of the lifetime cost of a large system. And one of the interesting things about maintenance is the way the activities break up within maintenance. The three on the right essentially have to do with figuring out what's there, and they amount to about half of the maintenance cost.
Right, because all the people that built the thing died or left or were fired or too hard to work with because they were cantankerous or going off to greener pastures. Yep, okay, did it. Good luck, guys. See ya. Did you document? No, not really. It's all in the code. You should see it there. It's fine. It should be self-explanatory, right?
Okay, so there are 3 vignettes about the scale of software systems that
figuring out what it is, how it's working, and then figure out the little quirks of it, and figure out what's going wrong, and then figure out how to fix it, and without breaking everything else, because it's been designed in such a way that they pass together every 2 weeks to fix a thing, and everything's all connected together. That's the other way. Nightmare. That's how they did it back then.
Let's look.
Still done today that way.
I'm not going to talk very much about development processes, but I want to note that there's a lot of attention right now to getting control of the development of software. This is the capability maturity.
Yeah, because all of them were stuck because they were all trying to schedule everything out. We're not the expected productivity, and stuff was just yeah, they had problems back then. This is right around the time when Agile was about to be introduced. People were like, "Oh, you have to keep it more flexible. It's about the people, not the process." And we can't document everything because it's taking us 10 times long to document and redocument and change document than it is to write the damn code. Yeah, all that stuff was bubbling around this time because they were stuck.
That came out of the Software Engineering Institute. It's a generally recognized 5-stage model that says your company gets better the higher up this chart it goes. You have development that is ad hoc and chaotic as you add more and more visibility.
Right, and as it is always in the beginning, because it has to be. Because you're just trying to find product market fit, you're trying to figure out what the problem is that you can bring a solution to, that somehow you get some traction somewhere to get in there, and without going broke or going homeless.
Processes and control over making the activities repeatable, you climb higher and higher until you get to be very, very good. Now, the phrase software engineering often refers to those activities. I'm trying to make a distinction. This is the management of software activity. I want to use the word engineering to refer to the technical engineering side rather than to the organizational side.
All right.
But you will find often the phrase software engineering used to refer exclusively to this activity. And I put this up here in part to call out that ambiguity in the use of the term. So current practice in software engineering sort of looks like this. There's a current strong emphasis on management control.
Yeah.
To stabilize the processes.
This is right before Agile. This is right around the time Agile is getting like, okay, we have to get out of this, guys. We're stuck. And this guy's like, and she's describing what it was like right before Agile became, it just, even though Agile got screwed up and messed up, totally back to this again. But this is the environment.
To provide visibility through standardization And in that capability maturity model, there is not a lot of concern for
they're trying to do production line systems onto software, and they were like, why isn't this working? Why isn't this working? It's like, well, I guess it's never going to work, man. I know, it sucks.
the technology for software production until you get to the higher levels. The basis is in empirical models rather than scientific models. That is, models that are based on observation and the assumption that if you do the same things the same way the next time, that the behaviors will be very much the same. Which is
like a factory? Oh, so your MBA guys are in there with the management? We're going to have management, business administration. All businesses are the same. I learned at Harvard. They told me that every business is just making widgets, except for software. Software, we're trying to figure out what widget to make. Like, what problem are we making a software machine for to solve? And is this the best way to solve it that the customer likes? Or no? And can we change it in a way the customer likes it? And can we make it easy to change so we can respond to what their customers? Because other people are doing stuff. It's not just us out here, by the way. It's other companies are trying to go after that same guy, that same customer. And are they listening to what the customer? They got something new, something better, something easier, something more fun, something cheaper that we have to now compete with and get where we fit in. This is it, man.
Is the setting in which empirical models work well for you. And it's focused a lot around so-called methodologies, which my friends tell me is a misuse of the word methodology, but there you are, which are prescriptions for activities. So, where is software engineering in all of that? Well, it appears to me that software engineering is in many organizations still essentially craft.
Yes, and it's always going to be craft because it's some tinker guy that rose up through the ranks of doing those 10,000 goddamn experiments with all these failures. Not failures, experiments didn't go the way they thought it was. And tweaking, listening to your customers, showing to people go, oh my God, that's terrible, that sucks, you're stupid, why would you do that? And all of a sudden one guy goes, oh my God, you're a genius. And then it's like, oh, who's that guy? Oh, he's in this thing over here. And it's like, there's a bunch of guys over here. And if you tailor your thing and you go through the process and now you're at this company and you're trying to upgrade your system for this thing. And they're like, you're a jerk. You want to destroy what we have and make us unprofitable because you're ass. It's like, no, man, I'm just telling you, I'm trying to find a better solution. It's like, get out of here, you. They get into jobs or was. Get out of here, you. We know what best. That's been the whole thing. So yeah, the craft people have a tendency to go off, get kicked out and go off on their own and put these things together, and they're the ones proposing the solutions because it's so painful, the process of trying to find, first of all, a problem that people want to have solved, that you can do something with the skill set you have, which is, if you're watching this damn channel, this is going to be computer software engineering development. And then a way to charge that, people to charge that, where you can do it for a sustainable thing. This is not a magical thing. This is just, where do you think this comes from? No, we're going to go hire some amazing developers. They've been at IBM for 27 years. This has been on the ticket after ticket after ticket after ticket. Like, you're not going to get your innovation there that can change the system. That's not what they're there for. Come on, man.
And in fact, an increasing number of organizations, it's becoming stable commercial practice. So I take software engineering at large to be climbing that first hump from craft into commercial practice, with some companies over the hump and some companies not started yet.
It's always going to come from the
craft,
man. It's always going to come. We're going to need, when it goes to be commercial, we're going to need people who are good at running through the tickets. Yes, I've done a lot of that. But I've also realized that I'm the kind of person that can find a new problem to solve somewhere else. And a lot of people are just like, no, I just want to punch the ticket and go on vacation and raise my kids. And I get that, man. I get it.
You can call out some of the instances where there is good, solid, well-established science underlying the business that we're carrying out, but there are not a lot of them yet. That's where I think.
I think there will be.
So how do things improve? Well, I said earlier that
it's Chris from the future. We still don't got it.
Deficiencies in practice, problems in practice often stimulate an engineering discipline. And Fran Allen spoke this morning about cycle from ad hoc solutions through science and back into practice.
Absolutely. It's all ad hoc. Come on, it's all ad hoc. We're in a new area. Look, man, if we're building motors, we got 10 billion examples of how to build a motor. We can pull one out for the sets and do it anytime. We're making new stuff. Software is about finding new problems to solve. Yes, it's all ad hoc.
The model is probably not terribly different from what's in this picture. We start out solving problems any which way we can.
So solid and UML and all that stuff, it all came with folklore. And all these packages came from OOP, alternative programming, C, all this came from folklore that got codified. Then we create the models and theories. It wasn't the models and theories first, it was the folklore, then the ad hoc solutions to the folklore, to the codification, and then we get the models and theories. It's like, and then people bring it out, oh, this is the only way.
Find things that work.
This is the only way to do it. It's like, no, it's just one way, man. And then people get confused, like, this is the only way. This is an engineering practice. It's like, no, man. No. We're continuously trying stuff new that's not in the codification. That's not in the model. That's not in the theory. Because we're trying to find new problems to solve. Because all the problems that I currently have been solved or are being solved in some other way. We're trying to fix them. Do something different.
Work pretty well. We start telling them.
We're going to have part 2 of this damn thing. All right. Here we go.
To each other. And at first we tell them to each other in back alleys and over beer. And
yeah, because it's your friends and buddies and pals that are into the same goofy shit you're into. It's not like, oh, we're going to create the computer industry. It's like that card player. If you're playing Magic the Gathering, like, we're going to create a whole new genre of card playing games. It's like, that's not what they were doing. They're like, oh, I got a Gigazord and I'm going to upgrade it by doing your thing. It's like, that's how they came about. They're playing, goofing around. And everybody's like, hi, man. And then that thing went through the evolutionary process. And then it came something else, and came something else. And then people spun off on that. And there's a bunch of people experimented with all kinds of shit that never went anywhere, that nobody cared about. That was like, that's stupid. We don't care. And then, but there's just this one thing, and we all like, oh, it's the one thing. It's like, no, there was a billion things.
Not respectable, but you say, well, if you do it this way, okay. And eventually, we sort out from the folklore those things that work pretty well.
Yes.
And the things that we work pretty well, we can talk about in public places, like conferences and classrooms.
Yeah.
And we get them organized so we can present them as bodies of information, and now they're starting to be codified.
Right.
Well, as we start to organize them,
a lot of this stuff is low-hanging fruit. A lot of stuff would have been found by somebody, and the fact that somebody like promoted it, took the time to promote it, that's the only reason we know about it. Like Liftoff principle. If it wasn't for Uncle Bob pushing it, needing an L, he needed an L. He needed to write out a word in his acronym. I got an S, I got the O, I got the I and the D. I'm looking for. He called his friend. Do you have an L? You anything else? Like, well, I got this Liskop. It's like, oh, it's just like interfaces. Oh, well, I could put the L in there. We're gonna make it. If it wasn't for that, we wouldn't know anything about Liskov substitution. Come on.
We're trying to find the right abstractions and the right explanations.
Sales.
Out of that come models and theories, and here's where the science grows. And when you get the science, you have two things that happen. One is that it can improve practice. As Fran said, sometimes it's hard to get it plowed back around. Sometimes it's hard because the models.
Yeah, because most people don't care. A lot of people about a lot of bullshit. A lot of people talk out the side of their neck about a lot of this stuff. It's like, no, it's the most amazing thing ever. It's going to solve all your problems. And then it's like, oh, really? It's like, he's a great talker, like Boots, right? He's like, this is great. It's a UML. So if I just codified, I'm going to put this into an engineering practice. It's going to solve all our problems. If I put it in the IDE, and Microsoft's like, yeah, put it on the IDE. It's going to solve all the problems. We try it out. Oh, the problems aren't solved. Damn it.
Stop there, rather than converting the models to say, not just in principle, this is how it works, but rather, for this situation, this is what you do. And that's a big step and an important one. But the existence of the models and the theories, and to a certain extent the improved practice, generate new problems that are bigger problems. And those problems you solve any which way.
Object-oriented programming, anyone?
And here we go again. So it's a cycle that spirals, we hope, up.
Well, it just spirals. And sometimes it dies. Sometimes it doesn't spiral. Sometimes it goes inward on itself. Sometimes it collapses. Sometimes it's abandoned. Most of the time it's abandoned. The spiraling is like so we see the success, but we don't see the billions, like guys that just washed out, failed, done, cut off. And when these companies fail, it's like there's a big announcement. It's like, no, we're just not. You just don't hear about them anymore. Not this continuously spiraling upward.
Let me take a whirlwind tour of the history of software development. I don't want to dwell on this. There's a familiar distinction between so-called programming in the small and programming in the large, and I want to reach back into the depths of the past and extract a previous stage that I'll call programming any which way.
All right, I'm gonna continue this on I'm gonna continue this on the next one. I'm gonna make a part 2. Excuse me. And thanks for listening to me rant. And I'm gonna continue this on part 2 as I keep repeating. And I'll talk to you later.